Hello everybody, let me present you the following poster. Fabrication of porous titanium 25 tantalum and boron alloy by powder metallurgy. I prepare for the 33 International Materials Congress held in Cancun, Mexico in 2025. Let's have a look at the abstract. So the titanium 25 tantalum alloy has been shown to have the best combination of properties for biomedical application in comparison to the widely used titanium 6 aluminium and 4 vanadium alloy. However, the main disadvantage is its poor wear resistance. Then it cannot be used for bearing applications. So, to overcome this disadvantage, the addition of boron is studied in this work, with the aim to improve the hardness of such alloy. To reach our objective, mechanical milling was used to fabricate the titanium 25 tantalum and boron alloys. Boron was added in 3 different quantities, 2, 4, and 6 atomic percents. The powders were milled during 24 hours under dry condition in a high-energy ball mill, a model SPEX 1000M, at 1725 rotation per minute, by using into an alumina container with 2 alumina balls of 12.25 millimeter diameter. Well, then the mill powders were put into an 8 millimeter stainless steel die and pressed at 400 megapascals. Well, after that, the green compacts were then sintered at a temperature of 1260 degrees Celsius, and that during 1 hour and under an argon atmosphere. Well, the microstructures of the sintered compacts was observed by scanning electron microscopy and also determined by X-ray diffraction. The result shows that the addition of boron improves the compactation behavior by reaching higher relative densities as the quantity of boron is increased. On the contrary, during sintering, the addition of boron reduces the densification with respect to the sample without boron, of course, except for the 2% atmosphere percent of boron. Well, after sintering, the compacts with around 20% of pores were obtained, and the microstructure of the sintered compact was composed of 3 different phases. So we observe that we have beta titanium, alpha titanium, and also we have titanium boron. So the microhardness of the samples with 2% of boron were improved by 50% with respect to the one measured for the example for the titanium with 25 of tantalum alloy and for 900 and 600 Hz respectively. So those values are larger than the ones reported for alloy fabricated by casting, for example, which is attributed to the effect of the powders milling that induce a hardened on the powders. Well, let's have a look at the experimental method. So we followed several steps. First of all, we had the initial powders. So here we have the titanium powders, the tantalum, and the boron powders. Well, the initial powders were weighted to obtain a stoichiometric ratio of titanium 25 tantalum for 50 grams of the alloy. Then boron is added in 2, 4, and respectively 6% in the titanium 25 tantalum alloy. As a second step, we have the powders put into the container with 12 mm diameter stainless steel balls. The milling time of the titanium 25 tantalum was 24 hours, and the additional 2 hours were used to mix the boron with the tantalum 25 tantalum alloy. On the third step, we had a uniaxial compaction of our samples. We can see here our samples with a diameter of 8 millimeters and a height of 4 millimeters. So we use this uniaxial compaction machine, and we use a 400 megapascals pressure. See? As we also use a vertical dilatometer. This for the sintering step. The sintering were realized at the temperature of was done at the temperature of 1260 degrees Celsius during 1 hour and under an argon atmosphere. For the microstructural characterization of the sinter sampled, we used the X-ray diffraction, the same observation, the electron microscopy, and some microhardness tests. Well, let's have a look at the results. First of all, we have in here some electron microscopy images. We have for the different samples in here, for example, we have the titanium 20% of tantalum. In here we have titanium 20% tantalum with 2% of boron. In here we have titanium 20% of tantalum and 4% of boron. And in here is the image for the 6% of boron. And what we can observe is that we have irregular shaped powders with a large particle size distribution lower than 45 millimeter, and this was obtained after the milling. If we have a look at this this graphic where we have the relative density versus time and temperature, and we observe this these curves, the electrometric curves, we can see that the relative density depends on the green conditions being higher for the samples with larger boron addition. The sample is a higher boron addition. All right. If we look, we have a look at this graphic when we have the densification rate versus temperature. And we have a look at these curves. We observe that the titanium borides are formed around 1000 degrees. And in this graphic, where we have the densification rate versus time, we conclude that the densification is inhibited by the boron addition. Well, if we have a look at this graphs where we have the pressure in megapascal versus the relative density, well, for the different samples with different percentages of boron added, we've seen that the relative density increases as the boron addition does it too, and that the smaller particle, well, they fill the interparticle pore and they generate a larger initial relative density. Well, in here I'm showing you the Pinelli Philo equation. In here A is the compressibility constant, and larger values suggest better plastic deformation. And if we have a look here of this graphic of this Pinelli Philo equation with for the different samples, we observe that the boron addition improves the plastic deformation during a compaction process. All right, let's have a look at these images for the different samples. Titanium 20% of tantalum, with it means no boron addition. In here for the 2% of boron, in here 4%, 6%, and In here we observe that the porous samples are obtained after sintering. If we have a look in here, we will see different pores with different dimensions. All right. If we have a look at these images, for example, in here we have for the sample without boron, and in here for the sample with 6% of boron, and we observe that the lamellar titanium tantalum microstructure, and here we had the titanium tantalum microstructure lamellar, is reduced by the boron addition, because in here is we can clearly observe it, and in here only small lamella are left around the sample. If you have a look at these EDS graphs, see the energy space spectroscopy, and analyzing the peaks we obtain for the different, for example, we have the alpha, the beta for the titanium of, and we concluded that boron titanium stabilization and formation of titanium boron increases for larger quantities of boron. So here we have the different percentage of boron sample for the samples. In here it was the sample with no boron, and in here we are increasing the quantity until we get to 6 for the sample with 6% of boron, and we've seen the different peaks. All right, if we have a look at the microhardness results, microhardness test, and the results we obtain. In here, for example, we have the microhardness, and what we could observe was that microhardness is improved by the formation of titanium boron, and we also obtain higher values of microhardness that we concluded that are due to the milling process. Well, let's have a look at the final conclusions. So the porous materials of titanium 25% tantalum with boron were successfully fabricated by press and sintering. The compressibility of powders was enhanced by the boron addition, and this is due to the large particle size distribution and also by plastic deformation. The sintering kinetics showed that the formation of titanium boron during the heating stage will reduce the densification rate. Also, we have said that the lamellar microstructure obtained for the titanium 25% tantalum was modified by reducing the length of lamella as boron addition was increased. The microhardness values were improved by the addition of boron thanks to the formation of the titanium boron phase. And the last conclusion was that the porous titanium 25 tantalum 4% boron samples was the most promising for the bearing load applications, for example, for the bone implants. And therefore, future research is in progress to evaluate the behavior of such materials under wear and corrosion condition as we need for the biomedical applications. Well, thank you all for your attention. Goodbye.